Okay, autonomous equations and section 6.5 or 2.5 and dy dt f y and t. This is non-autonomous. Right. So autonomous means that on the right side we have a function of y and there is no t. Now I will solve these two examples or versions of these two examples and you will see what happens. And if we have a function which is degree 3 or let's say even degree 3, it's not easy to find an explicit equation. For these two, we can find explicit equations for y. So let's do those two examples. These two. Okay, so this is telling me that the rate of change of y is directly related to y. So it's some constant times y. But in many situations like population dynamics, this can happen and that r is like rate of change, some kind of rate of change. But anyway, let's see, this is separable. So, and the simplest separable we have, so we have dy over y. Don't bring this one here, so leave that r over there, dt. And let's say we have y at 0 is y0. So we have 1 over y dy r dt. Well, let's write the constant here. So on this side I have ln absolute y is rt plus c, and this gives me absolute y is e to the power rt plus c, which is e to the power rt, e to the power c, and that is this, let's call this b, so it is b e to the power rt for some b. Okay. If I remove the absolute value, I come up with this simple equation and b constant. Now, if I apply the initial condition, y at 0 is b is y0. From here, y at 0 is simply b. So this tells me that y0 equals b. So the equation becomes y equals y0 e to the power rt. Okay. So let's discuss this equation and then I will do the other one. So, case 1, r is bigger than 0, this is called exponential growth. So we have y equals y0 e to the power rt, and it looks like this. It starts at y0, wherever y0 is, and it grows exponentially. In case 2, r is less than 0, that's exponential decay. And this looks like this. Okay, so in different situations we can have either of them. Even for population growth, we might have population growth or population decay. There are some, if you use this for population growth in countries, there are some countries with negative R. So the population in those countries are going down. Anyway, so this is the simplest autonomous equation, and that's how we solve it. Now let's do the other one. So number 2 was dy dt is, let's just solve the simplest one, no constants here, and y at 0, let's say it is 1. Okay, so this is a separable again, and we have dy over y times 1 minus y is simply dt on this side. So the integral 1 over y times 1 minus y dy is integral simply dt, but let's say the constant here. So what is this? This is integration, let's 1 minus y equals a over y plus b over 1 minus y, and this is equivalent. This is partial fraction, so if I add these two, I will get 1 over y times 1 minus y is the same as a times 1 minus y plus b times y over y times 1 minus y. So this gives me 1 is equivalent to a times 1 minus y plus b times y. Now you can solve it using any method, but the simplest for this one is, say if I have, let's say y is 0, then this gives me a is 1, and y is 1 gives me b is 1. So if you put y0, this will be 0, you can find a, y1, this will be 1, and then you can find b. Okay, so this gives me 1 over y plus 1 over 1 minus y. Okay. So the integral of this one will be, let me erase this partial fraction. So I have integral of 1 over y plus 1 over 1 minus y dy, and on this side I simply have t plus c. Okay, so this one, 1 over y dy, 1 minus y dy, and t plus c. And this gives me plus ln of absolute 1 minus y is t plus c. Okay, now this is ln plus ln. Sorry, this one is minus. There's a minus here, so this is minus. That's minus. Let me write this here. Integral 1 over a y plus b dy is simply 1 over a ln of a y plus b. Okay, so this 1 over a is here, so that's 1 over negative 1, so that's minus. So ln of y minus ln of 1 minus y, that gives me ln of y over 1 minus y. We just need one absolute value for this, and t plus c. So this gives me absolute value 1 over 1 minus y is e to power t plus c, which I write it as e to power t times e to power c, which is again like b e to power t. Okay? So, if I remove this absolute value, for this one, b should be positive. Without absolute value, b can be any constant. So let me continue here. Let me just erase this upper part. Okay, so y over 1 minus y will be b e to the power t, b in constant. Okay. So let's solve for y. We can do that here. So y is b e to the power t, 1 minus y, and that gives me y is b e to the power t minus y b e to the power t. So solving for y, this gives me y times 1 plus b e to the power t is b e to the power t. So y is b e to the power t over 1 plus b e to the power t. Okay? Now let's apply the initial condition here. I have y at time 0 is 1 half. So y at time 0 will be b here and 1 plus b is 1 half. So this in fact gives me b is 1 and y will be e to the power t, 1 plus e to the power t. Now if I divide both numerator and denominator by e to the power t divide, I will get a simpler version of this. Well, it's not simple, but it's much nicer. So then, with y at 0, 1 half, I found this nice function. And as t goes to positive infinity, this goes to 1. As t goes to negative infinity, this goes to 0. And it's 1 half at 0, and it's symmetric with respect to that point 0, 1 half. Yes, sorry, yeah, 0, 1 half. So this, it looks like this. So it has an asymptote here at 1, another asymptote at 0, and it's 1 half here. Okay. It looks like this. So this function is called sigmoid. As you see, this function, its range is between 0 and 1. And it's 1/2 at the 0. This is used extensively in machine learning as an activation function. Now, why? One reason is that it can be, I mean, probability can be modeled using this function because it's between 0 and 1. Okay. And also the derivative is just y times 1 minus y. That doesn't depend on t. That's also another reason. So, this is, that was the simplest example. Now, let's try another one which has more than, I mean, the right-hand side is of degree more than 2, and see what happens. Okay. So let's say dy dt, it is another example, 3 say, and normal I can say it on this side y times 1 minus y times, say 2 minus 1, something like that. So we do the same thing. We say, okay, then it is separable, and I have dy over y times 1 minus y, 2 minus y is dt. So again, partial fraction, I have 1 over y times 1 minus y, 2 minus y is a over y plus b over 1 minus y plus c over 2 minus y. So that is, well, let's write equivalent because that's the same. That is a times 1 minus y, 2 minus y plus b y times 2 minus y plus c times y times 1 minus y. And the denominator is y, 1 minus y, 2 minus y. So 1 is equivalent to a times 1 minus y, 2 minus y, plus b times y times 2 minus y, plus c y times 1 minus y. We can do the same thing again. This should be, the equivalence means this should work for any y. So if I say y, let's put y0. y0 gives me 0 here, 0 here, so a, and 0, 0, so a will be, so that's 2 times 1 and 1, so that's 1. Y equals 1 gives me y1, this is 0, so b times 1 times 1 is 1, so b is 1. And the y equals 2, this is 0, and this one will be 2 times 1 minus 2, that's minus 1, so that's minus 2, so this gives me c is minus 1. Okay, so let's go back here. So I have these three, so I have integral a is 1/2 over y dy plus integral minus, let's write this way, minus 1/2, 2 minus y dy. And on this side I have integral dt plus a constant. Now, let me double check to make sure that nothing goes wrong. So, that's correct. So y0 will give me 2 times 1, a, that's 1/2, y1, that's 0, that's 0. 2 minus 1 is 1, 1, okay, and y2 will give me 0, 0, and 1 minus 2 is minus 1 times 2 is minus 2, so that is minus 1. Okay, that's correct. So, let me erase this, continue. So, the three integrals, I have 1/2 ln absolute y plus ln absolute 1 minus y minus 1/2 ln 2 minus y. That's minus, so that will be minus sign. But this is minus and this is plus, right? Okay, so. And on this side I have d plus c. Now you might say, okay, let's put them together. If I want to put them together, then this 1/2 should come here. So I have ln of 1/2 minus ln of 1 minus y plus ln of 2 minus y to the power of 1/2, and that's d plus c. Yeah, I can put them together, that's okay. So that's ln of absolute. Okay. So on top we have this one times this one, so I have y times 2 minus y absolute 1/2, and this one is simply 1 minus y. On this side I have d plus c. Okay. So this gives me y times 2 minus y 1/2 over 1 minus y equals t plus c. Yes, sorry. E to power t plus c, e to power t plus c, which is in fact some constant b e to power t. Now, you might say, okay, well, that is a solution, that's correct. That is a solution. But can I find y explicitly? Can I solve for y? Well, it might happen if I have, like this one has 1/2. So which means that I should square this thing, say, to get rid of this 1/2. This is okay, square is okay, then this one is squared, then I have some equation in y which is not easy to solve. So most often these equations are solved numerically, and we do not really bother finding y explicitly as a function of t. So if it's, as you see, this is just degree 3. I might have degree 4, 5, 6, whatever, and that will be even more complicated than the formula here. But it should look like this. So we have some y's up and down, numerator, denominator with some power, blah, blah, blah. That's it. Okay, so what we are interested in is something else. And that is whether this solution is stable or it's not stable. So let me erase this thing and tell you what stable means. Well, I'm not going to discuss stability in full detail. That is something, if you ever study mechanical engineering or in some area of engineering, you might need that stability at some point or studying stability. But anyway, so let's look at those two equations we had. Y equals the first one, the decay and the growth. So I have y equals, what was it? So it was, say, b e to the power rt over that was in fact y0. y0. And when r is bigger than 0, I had something like this. As time passes, the solution gets larger and larger. So whatever that system is, at some point it might break down. So this is not stable. This is not stable because as t goes to infinity, the response of the system, whatever that is, its displacement, its velocity, whatever, that goes to infinity. So the system just breaks down. So this is not stable. Now let's look at r less than 0. This one starts somewhere and then goes down and goes to 0 basically. This goes to 0. But let me give you an example, a simple one. So it's e to the power minus 2t, right? So this r here is minus 2. Okay, and the y0 is 1. So as t goes to infinity, this goes to 0. So this one is stable. This one is stable, and it has an asymptote. It has an asymptote, which is y equals 0. So our job, in fact, is finding out whether an equation is the solution, say, to an autonomous equation is, say, stable or not, and in what range are they stable. And what range we mean, and you will see, it depends on where it starts. That is the y0. And since these are basically functions of time, and time starts at 0, so we don't have to worry about what happens below 0. So all of them start at 0. So we have everything on this right side of the t-axis. Okay. So you have dy dt equals f of y, that's autonomous. And if I say fy equals 0, fy equals to 0 gives me critical points. Okay, so example was, remember the example I give you, dt y times 1 minus y times 2 minus y. So y times 1 minus y times 2 minus y equals 0 gives me y 0, y 1, and y2. So these are critical points. Okay. What does this mean? If I start at y equals 1, if my y0 is 1, then what happens? Basically, You see, I have dy dt equals 0 then. So what happens is I get something like this. So let me draw these 3 lines. And so this is line 0, y equals 0, y equals 1, and y equals 2. And this is time. And so, go to the left side. So we want to study what happens if I say start here, if y0 is here. If y0 is here, what happens to the solution? If, say, y0 is here, what happens? And if y0 is here, what happens? So we have to discuss the solutions for different values of y0. Okay? So, let's look at this. dy dt. What is this? This is in fact slope. Slope. This is slope of the function yt. Right, that's the slope. So for any t, say, dy dt for a given t, t equals t1, gives me, say if it starts here, then at t equals t1, I have this slope of the line tangent to yt. So this is yt. But you don't see any t on this side, but because it depends on y. It depends on y. Now it also can give me dy dt at t equal to 0. That one is in fact the important one. Yes, sir. T equals 0. So that is when everything stops. So here. So that's when t is 0. So this one is dy dt for t equals 0. Okay, but that is in fact, since on the right side I have y and not t, so I have to put the value of y at time 0 in this equation and find the value of dy dt. Okay, so let me erase this and try this thing here. So I know the critical points, and erase this too, so that we know what we're talking about. So, if y0 is between 0 and 1, what happens? Let y0 be between 0 and 1. What happens if y0 is between 0 and 1? Then dy dt, I just need the sign of this thing, not the exact value. But I can find it in terms of y0. I need the sign. I want to see if it is positive or negative. So, if y is between 0 and 1, then this is positive, this is positive, this is also positive, right? It's a number between 0 and 1. It gives me positive, positive, positive. So it is bigger than 0. dy dt bigger than 0 means that it starts like this. So if it's somewhere here, it should start like this. So the curve is tangent to this and it goes like this. Now let y0 be between 1 and 2. What happens to dy dt? Okay, so if it's between 1 and 2, this is positive. This will be negative, right? That's 1 minus y. So if it is 1.5, this is negative. But this is positive. Positive, negative, positive, that is negative. So if I start somewhere here, say, then the slope is like this. And the curve goes like this. Well, the third region is y0 bigger than 2. y0 bigger than 2, then dy dt. This is positive, negative, negative. So it's positive, right? So if I start somewhere here, then the slope is like this. So it starts and goes like this. So, which one of these do you think is stable? Stable means that as t goes to infinity, it doesn't go to infinity. First of all, this or this cannot pass line 1. Now, I will explain why, or you can just think about it, why it cannot pass. So if this one moves this way and cannot pass this 1 and is increasing, then it goes on, and this y equals 1 is an asymptote. So in the long run, this in fact approaches y equals 1. This one goes down, never passes this line, so it goes down to 0. I mean 1, sorry. How about this one? This guy here, ooh, that goes to infinity. So the same problem has a stable or unstable solution depending on where it starts, at what point it starts. So this one is unstable, stable, unstable. Okay. So that stability basically depends on the sign of this. Sign of dy dx, dt, sorry, at t equals 0. Or it is sign of f of y. Okay? At y equals 0. Y equals y 0. Okay? So the problem reduces to finding sign of a polynomial. Now in this case, a third-degree polynomial. For different values of y, in fact, at y equals y0, that is, you're moving y0 on the y-axis. So let's graph this thing. Let me erase this and graph it here so you can see the connection between these two. Okay. So how do you graph a polynomial? The simplest way is just find zeros of the polynomial, which are in this case 0, 1, and 2. So 0, 1, and 2. 0, 1, and 2. Then, depending on the sign of the leading term, depending on the sign of the leading term, we can graph it, and we don't have to really graph it correctly. I mean, just a sketch is enough. So what is the sign of the leading term? This is leading term here, positive. Leading term, negative. Leading term, negative, positive, negative, negative. This gives me positive. Okay. So that's the leading term. I don't care what it is, I just need the sign. So if that is degree 3, and the leading term has a sign positive, then it starts here. So it starts somewhere here, goes up, comes down, and up. Okay? So this is the y, in fact, and this is this axis is not important for us, but that's just the value of fy. So let's say this is just the value of fy. You can call it anything. Okay, so y0 is here. So this is like this axis. You see, this axis here is like this axis. This axis and this axis are the same. I could have graphed this thing here, so this would be like this. But anyway, this is easy, don't need that. So if x is, if y0 is below, I never discussed this one. If this is, y0 is below 0.0 here, 0.0, which is somewhere here, then this is in fact dy dt, right? So dy dt, that's negative. Negative means what? Here it means that the slope is like this, which means if it starts here, it goes to infinity. So this is also unstable. Right? How about here, between 0 and 1? So the slope is positive. Here, slope is negative, and then positive. Okay? Now, these are critical points. These 3 points are critical points. And we can see from this graph that here it goes from positive to negative, negative, positive, and this is in fact stable. This is also stable, and here unstable, and here it is unstable. So that is what happens for this one. Okay, so let me just ask you, what can you deduce here? What can you say? Well, here it is positive, here it's negative. So what can you say about these critical points? But when looking at this, you see the critical points in fact give us the asymptotes. The asymptotes, which you can see, this one is an asymptote. So, well, the other ones are not, but can be an asymptote. Like this y equals 1 is an asymptote. And so if it goes from positive to negative, what happens? Positive to negative, this one is stable, right? Which means this goes this way, this goes this way, so this one is stable. Okay? So this one is stable, which means here and here, if y0 is between 0, 1 or 1, 2, we have stable solutions, and they approach to y equals 1 as the asymptote. If it goes from negative to positive, it's unstable. So this is unstable. And this is also unstable. So 1 is stable, 0 and 2 are unstable, as you can see from this picture. So going from positive to negative, you can see why this happens. Positive means it goes this way, negative goes this way. So this line in between, which is y equals 1, from these two sides they approach this. But negative positive, it goes this way, it goes this way. So this right here, y equals 0, is not a stable, say, critical value. So stability, basically, when we talk about stability, we are talking about stability of the critical values, which in a sense means asking this question: is this y equals that critical value an asymptote? Okay, so you can even guess if it goes from positive to positive, what happens? Well, how does this happen? It happens if one of them has degree 2, for example. So if it is 1 minus y squared, then it doesn't change anything here. So if it is positive, then it goes this way, goes this way. So that is like semi-stable. So that on one side it is stable, on the other side it is not stable. Okay. Now to find, you can either like memorize this thing, or you can just look at this and draw some picture for yourself, and from the picture just say, I like the picture because it gives me more insight in what's happening than this one, which is like a problem in like college algebra. Just say, okay, this goes from here, here, and blah, 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 like that. So I prefer that picture over there, the top one, and using the top picture, you can discuss stability. Okay, so let me stop here and so I will start another section next time. Okay.